Hello. Today, me and my friend Tornike are going to talk about USB in general, USB 2.0, USB 3.0, and also USB 3.1. So let's begin with what exactly is USB. So first of all, Universal Serial Bus, or USB, is a standard interface for connecting peripheral devices to a host computer. With this connection, the computer sends or retrieves data from the device. USB gives developers a standard interface to use in many different types of applications. USB device is easy to connect and use because it's a systematic design process. The USB system was originally devised by a group of companies including Comac, Digital Equipment, IBM, Intel, Microsoft, and Northern Telecom to replace the existing mixed connector system with a simpler architecture. Next slide. USB was designed to replace the multitude of cables and connectors required to connect peripheral devices to a host computer. The main goal of the USB was to make the addition of peripheral devices quick and easy. All USB devices share some key characteristics to make this possible. Also, all USB devices are self-identifying on the bus. In addition, all devices are hot pluggable to allow for true plug-and-play capability. Additionally, some devices can draw power from the USB, which eliminates the need for extra power adapters. To ensure maximum interoperability, the USB standard defines all aspects of the USB system from the physical layer, mechanical and electrical, all the way up to the software layer. The USB standards is maintained and enforced by the USB implementers forum USB-IF. USB devices must pass a USB-IF compliance test in order to be considered in compliance and to be able to use the USB logo. Next slide. USB 1.0 was first introduced in 1996, but was not adopted widely until 1998 with USB 1.1. In 2000, USB 2.0 was released and has since become the de facto standard for connecting devices to computers and beyond. In 2008, the USB specification was expanded with USB 3.0, also known as super-speed USB. USB 3.0 represents a significant change in the underlying operation of USB. To simplify the experience for the user, USB 3.0 has been designed to be plug-and-play, backward compatible with USB 2.0. As for 2010, the USB standard specifies different flavors of USB: low speed, full speed, high speed, and super speed. USB-IF has also released additional specs that expands the breadth of USB. These are on-the-go, OTG, and wireless USB. Also, beyond the scope of this document, details on these specs can be found on the USB-IF website. Next slide. USB is a host scheduled token-based serial bus protocol. USB allows for the connection of up to 127 devices on a single USB host controller. A host PC can have multiple host controllers, which increases the maximum number of USB devices that can be connected to a single computer. A single USB system comprises of a USB host and one or more USB devices. There can also be 0 or more USB hubs in the system. A USB hub is a special class of device. The hub allows the connection of multiple downstream devices to an upstream host or hub. In this way, the number of devices that can physically connect to a computer can be increased. All the devices on a single USB must share the bandwidth that is available on the bus. It is possible for a host PC to have multiple buses which would all have their own separate bandwidth. Most often, the port on most motherboards are paired, such that each bus has 2 downstream ports. The USB has a tiered star topology. At the root tier is the USB host. All devices connect to the host either directly or via a hub. According to the USB spec, a USB host can only support maximum of 7 tiers. Next slide. USB 2.0 is an evolution of the USB 1.1 specification, providing a higher performance interface. Today's USB 1.1 connectors are full-speed cables will support will support the higher speed of USB 2.0 without any changes. Characterization that has already been done on this cable confirms this capability. Analysis that has been done by the electrical team suggests that the target of 480 MBS is achievable on USB 2.0. USB 2.0 will specify a microframe which will be 1/8 of a 1 MSEC frame. This will allow USB 2.0 devices to have small buffers even at high rates. Support of higher speed USB 2.0 peripherals connected to a hub assumes USB 2.0 hubs. The higher transmission speed is negotiated on a device-by-device basis, and if the higher speed is not supported by a peripheral, then the link operates at a lower speed of 20 MBS or 1.5 MBS as determined by the peripherals. Next slide. USB 2.0 hosts broadcast information to all the devices below it. Low speed and high speed enabled devices will only see traffic at their respective speeds. Full speed devices can see both their speed and low speed traffic. USB 2.0 works through an unidirectional broadcast system. When a host sends a packet, all downstream devices will see the traffic. If the host wishes to communicate with a specific device, it must include the address of the device in the token packet. The response from devices are only seen by the host or hubs that are directly on the return path to the host. There are, however, a few warnings when dealing with devices that are of different speeds. Low speed and high speed devices are isolated from traffic at speeds other than their own. They will only see the traffic that is at their respective speeds. Next. A USB cable has two different types of connectors, A and B. A connectors connect upstream towards the host, and B connectors connect downstream to the devices. USB cables have two different types of connectors, A and B. The A and B connectors are defined in the USB spec to prevent loopbacks in the bus. This prevents a host from being connected to a host, or conversely, a device to a device. It also helps enforce the tiered star topology of the bus. USB hubs have one B port and multiple A ports, which makes it clear which port connects to the host and which to the downstream devices. The USB spec has been extended to include Mini A and Mini B connectors to support small USB devices. The USB on the go or OTG spec has introduced the micro A plug, micro B plug, and receptacle, and the micro AB receptacle to allow for device-to-device connections. Next. Now let's talk about signaling. All USB devices are connected by a 4-wire USB cable. These 4 lines are B bus, GND, and the twisted pair, D plus and D minus. USB uses differential signaling of the 2 data lines. There are 4 possible digital line states that the bus can be in: single-ended 0, single-ended 1, J, and K. The single-ended line states are defined the same regardless of the speed. However, the definitions of the J and K line states change depending on the bus speed. All data is transmitted through the J and K line states. An SE1 condition should never be seen on the bus, except for allowance during transitions between the other line states. The actual data on the bus is encoded through the line states by a non-return to 0 inverted digital signal. In non-return to 0 inverted encoding, a digital 1 is represented by no change in the line state, and the digital 0 is represented as a change of the line state. USB has no synchronizing clock line between the host and device. However, the receiver can synchronize whenever a valid transition is seen on the bus. This is possible provided that the transition in the line state is guaranteed within a mixed period of time determined by the allowable clock skew between the receiver and transmitter. To ensure the transition is seen on the bus within the required time, USB employs bit stuffing. After 6 consecutive ones in a data stream, a 0 is inserted to force the transition of the line states. This is performed regardless of whether the next bit would have induced a transition or not. The receiver expecting the bit stuff automatically removes the 0 from the data stream. Now Tornike will proceed.
Thank you. So let's talk about USB 3.0. It was first released in 2008. The devices which are compatible to the USB 3.0 can theoretically transmit data at a maximum speed of 5 gigabytes per second. But specification shows that most hardwares are only optimized to transmit 3,200 megabytes per second. There are many advantages to using 3.0 instead of 2.0, so let's discuss them. As we mentioned, the maximum speed rate has been increased drastically. For example, in USB 2.0, the maximum speed was 420 megabytes per second, and in USB 1.1, that speed was 12 megabytes per second. The second advantage is the bi-directional full duplex data transfer. 2 of the 5 lanes are reversed for transmitting data, while another pair is dedicated to receiving data, meaning that USB 3.0 can read and write data at the same time at full speed. Previous USBs like USB 2.0 and USB 1.1 did not support bi-directional data transfer. Third advantage is power. The unit load has been increased to 150 milliamps and configured device can now draw up to 6 unit loads, which adds up to 900 milliamps. This is more by 80% comparing to USB 2.0 and leads to faster recharging and powering on more than 4 devices from a single hub. And the one advantage left is compatibility. USB, as Vakhtang mentioned, is backwards compatible with USB 2.0. So when you get a new USB 3.0 device or a new computer that supports it, your old device will be able to communicate with the interface. Naturally, it will do at USB 2.0 speed, but unfortunately, you won't be able to use 3.0 cable to connect to a 2.0 device. There are small disadvantages to using 3.0 USB. Users need to have, of course, 3.0 port on their system to make sure of the high-speed data. Naturally, all electronic devices had a 2.0 port in it, so some devices may not be upgraded to use 3.0 USBs. Magnetic hard disks are limited by their read and write speed corresponding to rotations per minute, and the USB 3.0 is incompatible with USB 1.1. Also, USB 2.0 has a maximum length of 5 meters, and USB 3.0 has maximum cable length of 3 meters, which is also a small disadvantage. Let's discuss the pins on the USB 3.0. As we mentioned, the communication is full duplex during super speed, and comparing it to 1.1 and 2.0, it was half duplex. The connector has the same physical configuration as its predecessors, but with 5 more pins. As we can see on the picture, there are 10 pins here. The V-bus, D-, D+, and ground pins are required for USB 2.0 backwards communication. And also we have additional USB 3.0 pins. The 2 additional different pairs are for super speed data transfer, and they are used for full duplex super speed signaling. The GND drain pin is for drain wire termination and to control the AMI and maintain signal integrity. So let's discuss the protocol which is used in the USB 3.0. There are 2 protocols mainly. One is UASB and BOT. It is considered that UASB protocol is way better than the BOT, but it is dependent on the hardware and the software that we use. The USB provides generally faster transfer speeds than the BOT. USB attached is used to move data from hard drives, solid state, SSDs, thumb drives, and so on. And we can see the comparison between the 3.0 UASB protocol and BOT protocol. Compared to the traditional BOT protocol, we can see that USB performs up to 70% faster read speeds and 40% faster write speed when it's at the peak of the performance. This was made possible due to ways that USB functions in comparison to USB bots. For example, the USAP works in parallel while delivering and transferring signals. That's why it's much faster than BOT protocol. So let's now talk about 3.1 USB, which was first released in 2013. So there are two main versions of USB 3.1. We have Gen 1 version and Gen 2 version. Gen 1 version is basically very similar to USB 3.0, while Gen 2 version can transfer, as you can see on the slide, almost twice as fast as USB Gen 1 version, with 10 gigabytes data over one lane using 128 bits encoding. So we can see that the Gen 2 version is almost twice as fast as Gen 1 version. There are, as with USB 3.0, there are some advantages which come with 3.4. For example, one is smaller form factor. USB 3.1 is slim, 2.6 millimeters in height. Also, it's reversible, so you can plug USB 3.1 with both sides. It also has alternate modes, built-in support for DisplayPort and video and 4-channel audio, which basically means that it allows streamlining to a single type of port, because one USB port now can be used to adapters and support HDMI, VGA, DisplayPort, and other power ports at the same time. And USB is also backwards compatible with USB 3.0 and USB 2.0. So let's discuss the architecture, which is built into the 3.1, which is dual bus system architecture. The USB 3.1 interconnect inherits core architectural elements from USB 2.0, although there are some segments which are augmented to accommodate the dual bus architecture. The baseline structural topology is the same as 2.0. The 3.1 connection model accommodates backward and forward compatibility for USB 3.1 or USB 2.0 devices into a USB 3.1 connector. Similarly, USB 3.1 devices can be attached to USB 2.0 connectors. USB 3.1 peripheral devices accomplish backwards compatibility by including both enhanced super speed and also USB 2.0 interfaces. The USB 3.1 host can have both enhanced super speed and USB 2.0 interface, which are essentially parallel buses that may be active in the same time. The USB also implements the enhanced super speed bus architecture. Its communication architecture that is comprised of the following elements. One is enhanced super speed interconnect. As you can see here, the enhanced super speed interconnect is the manner in which devices are connected and communicate with host over the enhanced super speed bus. This includes the topology of devices connected to the bus, the communications layers, the relationship between them, and how they interact to accomplish the information exchange between hosts and between devices. The second part is devices. Enhanced superspeed devices are source of sinks of information exchange. They require device and enhanced superspeed communications layer to accomplish information exchanges between a driver or the host in one or more logical functions. And the third one is host. An enhanced superspeed host is a source or sink of information. It implements the required hosted enhanced superspeed communication layer to accomplish information exchange over the bus. It owns the enhanced superspeed data activity schedule and management of the enhanced superspeed bus and all devices connected to it. We can see here it's the enhanced superspeed bus communications layer and power management elements. To explain everything, we won't have time for all day, so I'll try to go over the general stuff of what is going here. Basically, the rows, which are device, host, protocol, link, realize the communications layer of enhanced superspeed interconnect. The three of the leftmost columns, which are the host, hub, and device, illustrate the topological relationships between devices connected to the enhanced superspeed bus. And the right column illustrates the influence of power management mechanisms over the communication layers. Let's now discuss the protocol layer of USB 3.1. The enhanced superspeed USB uses 4 basic packets for each type or 1 or more subtypes. And the 4 types, as we see here, are link management packets. They only travel between a pair of links, for example, pair of directly connected ports, and primarily used to manage that link. The second one is TP, transaction packets, traverse all the links directly connecting to a host or device. They are used to control the flow of data packets, configure devices, hubs, and etc. Third one is TP, data packets, traverse all the links directly connecting to the host or a device. Data packets have 2 parts, data packet header, DPH, and data packet payload, DPP. And the fourth one is asynchronous timestamp packets, ITP, which are multicast on all the active links. All packets consist of 14-byte header followed by 2-byte link control word at the end of the packet. All headers have type field that is used by the receiving entity, which can be hub, device, or host, to determine how to process the packets. And all the headers include 2-byte CRC16. And the CRC16 is a cyclic redundancy check. That's an error detecting code commonly used in digital networks and torrent devices to detect accidental changes to raw data, which basically guarantees us that during the data transfer between the devices, the data won't be affected. Data packets include additional information in the header that describes the data block. The data block is always followed by a 4-byte CRC32 used to determine the correctness of the data. And the data block and the CRC32 together are referred to as the data packet payload. So that's the specifications that we wanted to discuss today about the different types of USBs. I hope you enjoyed the presentation. You can leave any questions you have in the comments, and thank you for paying attention.